Good morning, everybody, and welcome to our presentation. What we'll be talking about today is a seawater cooled system and how it can be used in a two-stage cooling process. On stage with me today, we have Malouin from Jetcool, we have Imran Latif from Brookhaven Labs, Denis Browne from Start Campus, and myself. My name is Gemma, and I'm from Alfa Laval. So why are we really here today? If you walk around the room, there's a lot of talk about liquid cooling. There's a lot of talk about temperatures. There's a lot of talk about power. And what we're interested in is helping today to share with you the experience that we found from running an analysis of a Start Campus, an existing data center, which Denis will talk about more briefly soon, and how you can use seawater and free cooling methodology to really enhance the sustainability to end up with a water-neutral site for consumption. Denis, would you like to give us an intro?
Thank you, Gemma. Hi, good morning, everyone. It's great to be here. My name is Denis from Start Campus, and we're based in Lisbon. And our data center, as you see here on the overhead, is in a port city called Sines, about 130 kilometers south of Lisbon. Our first building is a 20 megawatt building. That's a recent aerial photograph taken last month. It's rated today for 20 megawatts IT load, but we're turning that up and probably getting closer to 27, 28 by the end of the year. And on the foreground, you'll see the image of the seawater intake basin. That seawater intake basin was originally designed and built for a coal power plant. To give you an idea of the scale, because the photograph doesn't do it very much justice, you can see the outline of the seawater intake station to the left of the basin. That seawater intake structure is designed with 6 intake chambers. Each chamber can deliver 10 cubic meters per second. So that's about 60 cubic meters of seawater per second. I'm not sure what it's in the local language or the local currency, but it's a lot of water. We won't be using a fraction of that amount of seawater, but it gives you an idea of the sheer volume of seawater that we have available to us. We're also approved from the local power network for 1.2 gigawatt of power off the grid, and Portugal is a fantastic place for renewable energy off the grid. So the first building here is the first building of an entire campus made up of 6 buildings, and we're on to our second building. So this building today, we have deployed various different cooling options for the customers. We're basically agnostic to whatever cooling technology you want to bring in. So just briefly talk about the seawater. So the seawater we have an early seawater system installed to get this first building up and running. So if you follow the seawater from the seawater intake basin, comes up into the building here, and goes through the primary heat exchangers, Alfa Laval, best heat exchangers in the world. And from those heat exchangers, it leaves. And so it's done its work in the first pass through the heat exchangers. But for the immersion room that we have designed within the building, we have a dedicated immersion room within the building. We take a second use of that seawater as it's returning to the ocean, and we use it for cooling immersion tanks. The immersion tanks can take higher inboard temperatures, and we get a higher outboard temperature off the immersion tanks. That higher outboard temperature is used on the seawater, the clean seawater, which is a phenomenal facility, and we then push that seawater into a desalination circuit because we have enough temperature difference and clarity in the seawater to give us an opportunity to carry out the desalination with a low pressure, low temperature membrane system. And so the seawater then returns, and we're getting the opportunity to provide our own water for irrigation and for industrial use, not just for us, but for also from a neighborhood perspective.
Thank you. Thank you, Denis. So this is what the white paper that we've been working on is focused around. The shift from a predominantly air-cooled system, the benefits to moving towards a liquid-cooled plant, and the different steps and the different energy savings that can be seen from using a free cooling energy source. We'll go through some carbon savings that you'll see from using this type of system, and then you will also see the benefits of the two-stage optimized system as we go through. What we have here is a very simplified diagram system layout that has been integrated there. And what you can see is you can see the seawater being pulled going into the first heat exchanger at point A, then going into the air-cooled system. From there, as Denis just described, it moves further through the system, being used effectively twice. So you have very little pumping increase in terms of power because the main pumping extraction has already been done. You're effectively circulating the water through the second loop to then increase the heat and the temperature slightly further. And that is where you then gain the benefits from being able to use that heat and make it a much more viable heat source moving forward. Irrespective of that, using the seawater through these types of systems proves very, very efficient. You do not consume any water. It's a common misconception that when you take water from these systems, that you consume it. They don't. They are completely water neutral through this, and this is why cases like STAR are particularly interesting. So now for some numbers, and there are a lot of numbers on this slide, I appreciate that. If anyone has any questions, we'd be more than happy to take them at the end. We have gone through and done a thorough analysis of CO2 savings compared to a standard chiller-based system and the seawater extraction that we have. When we look at those solutions, we need to allow for pumping, obviously, of the seawater, which does incur an energy cost, but is in no way comparable to the CO2 emissions that would come from a standard chiller-based solution. The central graph shows you the flow rate that is taken out of the system. There are different ways that this can be approached. When you look at these solutions, particularly in seawater applications, it is imperative that design is optimized. You can do a lot, really, with very little water. The efficiency of the system, it combined with the approach temperatures that can be achieved across these systems, means that you can actually, when you switch more to a greater proportion of liquid-cooled versus air-cooled, actually reduce the water flow you're removing from the system. And this is what has allowed START to increase the capacity of what they are putting out into the market for their first stage by optimizing this water usage and moving forward onto the subsequent areas without any further extraction. Imran?
So as Gemma said, this is liquid cooling can do wonders. And in this particular case, we use the water twice, which happens to be the seawater. So it came in first and it took care of the air-cooled loads. And then instead of going back into the ocean, instead we use it for liquid cooling at a higher temperature, which offers a further higher temperature for us to be using it in a meaningful way for a possible heat reuse application. And during the process, as Gemma had mentioned, we were optimizing the flow. So the incoming water, which is also really important in this case, was also optimized, or in this case, it was reduced. So that really makes this whole system a really viable and sustainable system with a complete circular economy.
This paper is currently being reviewed and will be available soon for full review by yourselves. It'll be issued on a free paper. But what we just want to go through with you now is some of the conclusions that we've found from working within our team on this. Imran's already mentioned, liquid-cooled solutions can provide a real viable CO2 saving compared to a traditional chiller-based system. Water is inherently more efficient at transferring heat compared to air. We've talked about it. You walk around this room, there are lots of dielectric systems. There are lots of water-based systems. Fluid in itself is easier to take heat from and to remove heat to. But when we look at this, the optimized solution we have here with the two cooling solution, when you look around, everyone is talking about how do we design an efficient hybrid solution with air and liquid within our data center halls. And looking at it in this way and using your cool twice provides some additional efficiencies that can really be achieved through these types of systems. The reliability of the performance of these systems. A lot of people have come across seawater cooled systems in the past, and there have been issues. But if they are designed well, you need to look at maintenance. You need to look at the flow through the heat transfer equipment, whatever it might be. You need to encourage the constant turbulence and the constant conductivity and thermal transfer across these systems. By doing that, you can achieve a really thermally efficient design, which allows for minimized fouling and continued uptime of these types of systems. These water-cooled systems being worked in this way also support the high IT workloads that we're seeing being demanded across the board in every sort of area at the moment. These seawater systems could be river water systems, could be aquifer systems, could be canal water. There are lots and lots of water sources that are not currently being used to their best advantage. There are challenges in certain territories around the world. There is licensing rules that have to be adhered to, and those need to be taken into consideration. But when you look at the heat recovery, additionally, off the back of these systems, you can often actually put the water back into the water source at a lower temperature than what it was extracted from in the first place. And that really is a key factor when we look at these extraction licenses and what you can and cannot do. Imran?
So this is a great point Gemma has mentioned, because obviously we have to care about the planet as well. So the water is coming in, obviously is going to take the heat from the CPUs and the GPUs. So instead of going back into the ocean stream or the river stream, as Gemma mentioned, at a higher temperature, that heat can be taken out. And we have seen some amazing use cases, such as fish farming. So in Netherlands, they were using the data center heat to grow tomatoes in the greenhouses in the middle of winter. How cool is that? So we have another research coming up in a very short time. We will be actually deploying the heat reuse of this START campus, 100% sustainable campus, amazing place in Lisbon, Portugal, that will be taking that heat and will be doing an actual study to have it meaningfully used in a commercial application in the nearby facilities. So please look out for that paper. It will be announced on LinkedIn and other sources as well. With that, I am going to introduce Bernie of Jetcool, who's going to talk further about the advancement in liquid cooling and their technology.
Very good, thank you. As we look toward the future of computing with accelerators and higher power processors, we're seeing those power levels increase and increase. And the next step, right, for all of the things that we're talking about today is, how do you take that step, for example, maybe beyond immersion, to handle those higher power levels? How can you use the same strategies, the seawater cooling, to handle the higher power and still get the really high coolant temperatures for heat reuse or fish farming or desalinization, right? And so, that requires some other kinds of technologies to come into the portfolio. One of those are cooling technologies like Jetcool. Jetcool has a direct-to-chip liquid cooling technology. The basis of our technology is arrays of tiny little fluid jets that are targeting hotspots on the silicon. And for folks that are unfamiliar, feel free to stop by our booth here to see more of a technology demonstration. But in essence, that helps you to increase the efficiency. That's a good thing. It also helps you increase the performance to handle the higher power accelerators for AI. And what that means is it becomes a key enabling technology for, as chip level power levels increase, you can still achieve the high coolant temperatures. And we've done that for multiple applications. This happens to be one of them at San Diego National Lab, where we are cooling the cluster there with 60 and 65 C inlet coolant temperatures. So all of a sudden, that really gets that temperature level high enough that you can start doing the creative things that we're talking about here today with the seawater systems. Again, bringing that solution full scale basically from the sea to the silicon. And this is one technology that can help you get there.
We hope you've enjoyed listening to us this morning. As we mentioned, the additional paper will be released soon, and then there'll be some future work coming around what these opportunities for heat reuse might be. If you've got any questions, please feel free to either raise them with us now. We've probably got time for one very quick question, or if you'd like to come and speak to any of us at the end, we will be standing over on the other side. We hope you found this interesting. Thank you.